Hello. In this live stream, I'm gonna look at ways of exploring correlational data, and I think one of the best ways to learn R is to look at its functions and look step by step how things are done. So I'm going to be looking at some frequentist analysis, some Bayesian analysis, and ways to also visualize correlations using my typical toolkit when it comes to analyzing correlational data. So let's get started. First thing I'm going to do is load some of the libraries that I'm going to be using. One that I found recently is the correlation library, so we'll bring that up. I love using ggstatsplot for visualizing correlational data, just for visualizing any sort of data. This is a really, really nice package. dplyr, which you're probably familiar with for manipulating and cleaning up data sets. For Bayesian analysis, there are various packages. So for calculating Bayes factors for correlational data, but the Bayes factor package comes to mind. It's a great package. But when it comes to visualizing these sort of analyses, particularly the prior and posterior distributions, I really like JASP, which is point-and-click software, which is great. But what you can do is there is the JSQ package is essentially a port of what is done for the Bayes factor analysis on JASP. So I've installed it this way. I've already pre-installed this using this command here. By the way, I'm going to post this code, all the code that I'm doing afterwards. Anyway, okay, we'll load the JSQ library. And I also like doing robust correlational analysis as well, especially when you are dealing with smaller data sets that have outliers. You want to make sure that your results are robust, particularly to extreme values in your data set. So one thing I like doing, especially when I'm working with smaller data sets, is doing robust analysis. There are robust analysis functions within ggstatsplot and the correlation package, I believe, but I'm used to using the WRS2 package. So we've loaded those things, and we're going to be using a data set which explores a few variables related to mammalian sleep. I think this is a package that's within ggstatsplot. Let's load it. I'm creating a new object called dat, which is the data set. Just renaming it and sleep yet. So we're creating this. That's created, and then let's have a look by using the view command. We'll have a look what this looks like. Live streaming is always fun. Anything can happen. Here we go. We have various animals. There's 83 animals, their genus, and a number of variables such as sleep total, sleep REM, the hours that they're awake, their brain weight, and their body weight as well. So it's a cool little data set that we can do some analysis on. First thing is, let's do some correlations using Bayes R. And I believe it's core test. Yep. One thing that's always good to do is look at the help function to actually see what the heck is involved when you are using certain functions. So 2 question marks dot test, which is the name of the package. Enter that, and onto the right here, we should get there we go. It's part of the stats package, which is part of R, and it's got the arguments for what you need for the correlation test. So essentially 2 variables, X and Y, which we're going to be putting in, whether you have a two-sided prediction less than or greater than analysis, and the type of correlational method that you want, whether it's Pearson's, which is a conventional approach for doing correlational analysis, and a few other factors as well. Okay, let's do this. Core test, and when we look at our that data set, we can see the names of the variables. So let's look at brain weight and body weight. Is there a relationship between brain weight and body weight across 83 species of animals? So we're calling the data set, and then we're looking at this. Now, look at this. Once you put the dollar sign in, I don't know what the technical name for this is. Once you put the dollar sign in, then you can go down and actually find your variable of interest, or you can type it in normally. So we're remembering the function x, which is our first variable, y, and let's put this in body weight. There we go. And we will keep the other things as default. Running our test. There is our results. So these two variables seem to be highly related. We have the p-value, which is tiny, and the confidence interval, which is extremely large. But the first thing that we should have actually have done is looked at a plot. It's very important when you're doing these sort of analyses to look at the plot of the data to make sure there's nothing unusual, particularly in terms of outliers. So here we'll start off by using just the base plotting function, which is kind of boring, but if you want a quick and dirty analysis, this is always good to do. So it's plot, and then we can copy and paste what we had here. This is just saying plot x against y. Let's run that. And there you go. We have two big outliers. Let's zoom in. So there's two big outliers and a couple of other ones, but remember this is about 80 species. So it's difficult to know whether this relationship is actually dependent on these two big outliers, especially this big one up here. So there's one animal, probably an elephant, I'm guessing, which has, I think it's in kilos, 6,000 kilos, and almost a 6-kilo brain. So that is how we do things in base. But I want to make things a bit more interesting. Let's go back and reanalyze that data by removing some of these outliers. But what I want to do is I want to make this look a lot nicer. And to do this, I'm going to do ggstatsplot. Okay, so what I'm going to do is, with the command within ggstatsplot is ggscatterstats, I believe. Let's do these. I can't spell. Let's see if I'm right. There we go. So we're getting the help function up to see how to actually run this. So it's either Googling it or getting this, but this is, if you know the name, then this is a bit easier. Here we go. Okay, we can see the usage here. This is a fantastic package, and there's a lot of stuff that you can do for creating really, really great looking scatter plots. So what can we do here? Okay. Calling function, the data set is that x equals brain weight. Y equals body weight. So the default gives us, whether we need anything more than this. I'm not even sure if I have to specify anything else. What does it give us? And you'll see the huge difference between base plotting and plotting with something a bit more advanced. So this is like ggplot2, but even better with the sort of stuff that you can get. Of course, my laptop's being a little bit slow tonight, probably because I'm streaming. So that plus Chrome plus RStudio is making things a bit tricky. But we press on. What we can do is, in mind, there's also, if you're watching this on YouTube or on Twitch, and I think on Twitter, you can also write stuff in the chat and I'll be able to see it. That's one way you can participate. So let's go back. This analysis is still going. What is going on here? Okay. While this is going, it's either an error or my computer is just being ridiculously slow. If it's an error, maybe it's because I didn't specify this. Okay, still plowing ahead. Yeah, something weird's happened. All right, let's try this. Aha, yeah, I got to spell it right. Let's try again. Okay. Doing our analysis. Things are still going very, very slowly. Okay, there we go. We finally got there. We finally got there. Okay. Here we go. We're zooming this a little bit further out so we can see what's happening with our relationship between our two variables. If this ever loads, it's time for a new laptop, and I'm getting one in a couple of weeks, hopefully. Still loading. While we're waiting for that to load, we can see the plot down here, and of course, like before, we have our two outlier variables. It has finally loaded. Okay. Great thing about the GG stats plot package is that it gives you a summary of your analysis above your plot. So this essentially reiterates the analysis that we did from the very beginning for our relationship between these two factors. Number of pairs is 56, so even though we have 80 animals, it looks like there wasn't data for all the variables that we have here. What it also shows us is the distribution of each variable. So the distribution of brain weight and the distribution of body weight. Of course, this is highly skewed because we have this 1, 2, possibly 3 outliers here. What it also does is it calculates a base factor as well, which is something we'll be going into a bit more. Okay, still doing some sort of analysis. Come on, RStudio, catch up. What we're going to do now is we will remove some of the larger variables, because we can see that there's two variables, or there's two animals which have a high body weight or a very large body weight, which are potentially skewing our results. So what we'll do is we will use dplyr. So I'm creating a new data set called newdat, and the filter function within dplyr And the first thing we do is we specify the data set, which is dat. And the next one is our variable that we want to manipulate somehow. So this is body weight. And then we specify some sort of conditions. So we want to keep anything that's under 1,000. Stop this, hey? Okay. Oh, yeah. There we go. Let's see if we can try this again. And if not, maybe we have to start R again. This is great. Gotta love stuff that's live. It's probably not going to work. All right. Things are still looking like they're running very slowly. That doesn't stop them. We'll try restarting it. All right. Let's look at our to plot our new data. So we've got the new data, and we'll use the basic plot function. New. We remove. This is a very quick and dirty way of removing these particular outliers. So yeah, so now this looks a little bit better. There still are a few outliers. What we can do is let's just leave them in for now for demonstration's sake. Okay, so we have this analysis, and what happens if we run this again? What do we get? It's probably going to be similar. It's very strong. There we go. Yeah, like it's still a really strong relationship in this case. I mean, you can make the argument that these are some pretty big outliers, and we can remove some stuff. But yeah, there we have our results there. All right, next thing I want to do is some robust statistics. So let's see what is the impact of these potential outliers. What we'll do is let's go to the help. No, this is called. See if I can remember off the top of my head. PB core, I believe. Yeah, there we go. So this is running a robust statistical analysis, which sees what happens when you trim both ends in terms of outliers. Yeah, it's still very, the correlation coefficient is still very strong. However, if your correlation coefficient is small, and if you have small data sets, or if you have outliers which are probably influencing your analysis, I'd highly recommend running a robust correlational analysis. Let's go Bayes. Let's see. And I'm putting in an example analysis here. So this is using the JSQ package, and within this, so this is an exact copy of the same sort of what you can do within JASP point and click software, except this is getting exactly the same results and exactly the same plots. But if you want to do it in R, then you can do that. All right, we're going to get a new data set. So new. Do that of. Okay, specifying relationship between these two variables using a Bayesian approach. Now, the reason that a Bayesian approach is good is that it allows you to investigate the relative evidence for an alternative hypothesis versus a null hypothesis. If you get a non-significant result for your correlational test, it's impossible to know whether that's due to insensitive data or support of the null, no matter what the size of your p-value. But if you're doing a Bayes factor or a Bayesian correlation, you can look at the relative evidence. So you might be able to say there is 10 times more evidence, the data, there's 10 times more evidence for a null hypothesis than relative to the alternative hypothesis. So it's a really nice way, especially if you're interested in a null model. But on top of that, it's beneficial. One advantage of p-values is that the result is very intuitive. When you're doing correlational analysis, you have to rely on the correlation coefficient. Of course, there are, when it comes to the correlation coefficient, let me just, I think this is important. When it comes to the correlation coefficient, there are certain guidelines, or Cohen has suggested certain guidelines for what constitutes a small, medium, and large correlation. However, these things shouldn't be relied upon because they were originally designed to be a backup when you had no idea for what really constitutes a small, medium, or large effect in your field. So for interpreting your effect, you have to either rely on this, which isn't very accurate, but the thing I like about Bayes factors is the number is intuitive. So you can say that our alternative hypothesis, there's 10 times or there's 100 times more support than our alternative hypothesis relative to a null hypothesis. But let's have a look. Let's have a look at this analysis. Okay, one thing to specify as well is the prior width. And what I'm going to do is, I think it's a third by default, but I'm going to put this as 1. So this, once I visualize it, this is going to make sense. I wouldn't normally do it as 1, or I would never do it as 1, but I'm going to visualize something just to make a demonstration, just to give you a demonstration. Okay, and this is also going to be plotting some results as well, which I think is quite important and why I like using this package. The reason why I'm doing this live stream was actually, I was doing this exact same analysis earlier today on a data set. Let's run our analysis. Hopefully it doesn't take as long as the prior one, which, here we go. So we have our results here, and our Bayes factor is over 600. So this tells us, given our prior distribution, it's going to be wonky here. Yeah, let's try that again. So this tells us there is over 600 times more evidence for an alternative hypothesis compared to the null hypothesis. There's no relationship between these two variables. If we zoom in a bit here, the dotted line represents our prior distribution or our prior belief of what the correlation is. If we choose a prior distribution of 1, this assumes that we think a population correlation of -1 is equally as likely as 0 or as 1. And I just can't think, other than you doing something completely random, there's almost no situation where this will be the case, where a correlation of -1 would be equally as likely as 0 or 1. So this is a very unlikely prior, which you should almost never use for your analysis. But this visually shows you the distribution of your posterior, but also your prior belief. Let's rerun it doing something which is probably going to be a little bit more realistic, because when you're dealing with correlations, you would expect, in many circumstances, you would expect it to center around 0, and that for values closer to 0 to be more likely than values that are closer to -1 and 1. Let's adjust this to 1/3. Clear this. Run this again. runs our analysis with our different prior distribution, which is a bit more realistic. Now, our base factor is still quite large. So this demonstrates, and this is a good thing, that our base factor is not super sensitive to our choice of prior. One thing which is recommended is to demonstrate that your findings are robust under various prior distributions. If we have a look here for our plot, now we can see, remember before, our prior distribution was uniform, completely flat. Whereas here, we've specified our prior distribution to represent, this is a more, look, there are many ways that you can set a prior distribution, and this is just one, but this is much more realistic than what we had before. This suggests that, values or correlation coefficient values around 0 are much more likely than values that are closer to 1 or minus 1. Still, regardless, our base factor so this is a base factor for the relative evidence for 1, which is the alternative hypothesis, compared to 0, which is the null. You can also look at the inverse, which is the base factor for a comparison of the relative evidence